Okay, so welcome back from the weekend, grade 10s. So we really only have this week, so the lecture that I'm giving you this week, and this will be your last learning check attached to this lecture. Next week I'll still present a lecture, and I really hope that you guys take a look at it, but there won't be a learning check. So this will be kind of our final week with actual work, but it's still important next week that you log on and just watch the lecture. Okay, so just to recap what we talked about last week, we kind of finished up our different types of compounds. So we've gone through now ionic compounds and covalent compounds. This next thing we're going to be talking about is reactions. So we've already kind of addressed the idea of reactions when we talked about chemical change, because that's what a reaction is when something changes chemically. When something changes physically, like when it changes from, say, ice to liquid water, that's not a chemical reaction. You're not seeing a reaction there. What you're just seeing is a state change. Okay? So this next part is we're going to go through kind of reactions, and it's really going to revolve around the reactions of ionic compounds. We'll get into the reactions of covalent compounds if you take grade 11 chemistry, but like mentioned before, covalents are a lot more complicated than ionics. So we're going to kind of stick with the simple things first, and then we'll kind of advance. So reactions are, again, responsible for forming compounds as well as breaking apart compounds, changing compounds. So therefore, we need to know about the two types of compounds that exist, and we've gone through those, ionics and covalents. We also need to know how they form, okay, and we went through that in ionics. Covalents, again, we'll leave that until grade 11. Their formulas, so like how to make a formula for an ionic compound, and then how to analyze, say, a formula for a covalent, and then how to name them properly. Now, we need to know all those things before we get into reactions, because reactions is now kind of stepping up our game and kind of getting into a little bit more of advanced chemistry. So, just to move on, we are going to be using all of the kind of prior knowledge when we go through this. So it's kind of important that we understand at least ionics and covalents before we go through this. Okay. So here we go, chemical reaction. So again, a chemical reaction, if you kind of look at my picture over here that I have on the left, okay, it means that there's going to be a particle change. So here I had hydrogen particles, oxygen particles, and they reformed to make something new that they didn't have before, okay, and making a water molecule. Okay, and then here's another example of a reaction over here, okay, and again, the telltale sign, we're kind of seeing this on a macro scale here. You're seeing bubbles without heat, which would be an indication, a color change, all these things that a reaction happened. Okay, so our general formula for a reaction, okay, and I apologize, this thing's just a little bit too big, is basically we have a reactant plus a reactant, and sorry, this thing's kind of blocked here, makes a product, okay, and that's how we kind of write out reactions. We have a little something reacts with something, we put a plus sign in between them to show that these two things are combining. Then, and again, I'm sorry for the formatting, it's usually an arrow that you place and then the product. So down here is kind of an example of we have carbon plus oxygen, and then you would write, and let me get a better color here, I'll use black, an arrow to carbon dioxide. Now this arrow right here indicates that everything to the right of the arrow is the products, and everything to the left are the reactants. So these two things are reactants, and this is the product, or what you made. Right? That's one way of writing it out. Now we write it out in words. The other way we can write it out is just using their symbols. So we've got carbon, which is the C, plus oxygen. Now remember that oxygen's a diatomic, so it has to be written as O2. So there's a little 2 there, you can't really see it. And then that would lead to carbon dioxide. And again, there's a little 2 there, but again, the formatting is a little bit difficult. Now, if we were kind of to look at it, this is what pure carbon looks like. Oxygen gas is clear, so there's not really a good picture of it. And same with CO2 gas is clear. But there's kind of what the molecule would look like. Okay, now we're not going to go through this too much because it was addressed in grade 9, but the conservation of mass. So when you do have a reaction, you can't just have mass disappear. So if I use 6 grams of carbon here and 12 grams of oxygen, then I have to get 18 grams of carbon dioxide. Okay, it's not possible to get 17 or 15. You can't just have mass disappear. So it's the idea of conservation of mass. You're conserving the mass. Okay? And the rule is basically indicates that the mass of the reactants, okay, so 6 plus 12 is 18 grams, must equal the mass of the product. Okay, and the product is carbon dioxide in this case, or 18 grams. Now, there is some kind of examples where it tricks us, where we think, well, the conservation of mass isn't being followed here. So here's an example. Say I take this powder, which is 6 grams, and then I take another powder that's 12 grams, and we end up with 13 grams of this powder. And we're like, well, where did the mass go? That's impossible, because technically you're right, it is impossible. But what happens sometimes is some of the mass will go off as a gas. So it could have released some CO2, or it could have released some oxygen, or it could have released, say, some water vapor. And if that goes off as a gas, it escaped. So there must have been, in this scenario, about 5 grams of gas that went off, because it has to add up. This adds up to 18 grams. This must add up to 18 grams. And if I only have 13 grams of product here, that means that 5 grams of it must have escaped as a gas. Okay, so there's no way that you can eliminate mass. So also, we're not going to focus too much on this in grade 10. We will in grade 11. So since the mass of the reactants must equal the mass of the products, you have to make sure that the number of atoms in the reactants must equal the number of atoms in the products. And that's the idea of balancing. Okay? And we went through that in grade 9. We're not going to focus on it too much because it's not really a skill. It's kind of just something that we do as trial and error. But that's the idea of making sure if I have 1 carbon over here, then I can only have 1 carbon over here. And if I have 4 hydrogens on this side, I need to have 4 hydrogens on this side. And if I have 4 oxygens on this side, I need to have, here's 2 right here, and then I have 2 more oxygens on this side. Okay, and that's the idea of balancing, and we put these numbers in front. We're not going to focus too much on balancing because we'll talk about it in grade 11 if you go on. Okay. Now we're going to get into the reactions. Now there's only really 4 types for ionic. And I really kind of should put on here ionic reactions because they're really going to kind of focus in on ionic compounds. And they can't just happen sporadically. There's kind of rules that chemicals have to follow when they perform reactions. And there's really 4 types. There's a synthesis reaction, a decomposition reaction, a single displacement, and double displacement. And we're going to go through these 4 briefly today. And that's going to be the primary focus. So the first one we're going to talk about is a synthesis reaction. Well, this word should indicate what it's doing, okay? When you synthesize something, you're producing something, you're making something. So these are kind of things that where you are going to make something more complex from simpler blocks. So it's the idea that you're going to take A and B, 2 simple things, right, like elements or very simple compounds, and you're going to combine them to make something more complex. Okay? It's sometimes also called a combination reaction or a formation reaction because you're doing both of those kind of things. And the general equation is, A plus B leads to AB. Now, this is what happens naturally. If you take an element and you isolate it, like say I isolate some iron, okay, it's automatically going to react with oxygen and then go back into the formation of a compound. This is how compounds form all the time. It's just synthesis reactions. Okay? So here's an example of a synthesis reaction. Now this isn't an ionic one, but it still works. And it's the idea that these hydrogens are going to combine with oxygen and make something more complex. So we have simple, simple, going into more complex. Another example of a synthesis reaction, although it's a little bit tricky to notice it is one, but we'll talk a lot more about this in grade 11, is whenever we burn something. So whenever we burn something, we take, basically, this is an example of a fuel, methane plus oxygen, and we make CO2 and water. Now, anytime that you burn something, in 99% of the cases, these are the 2 products that you make, is carbon dioxide and water. But we're not going to focus too much on this. We're going to kind of just move on, because we'll talk about combustion a lot in grade 11. Okay, now the exact opposite of synthesis reactions is a decomposition. If you think of things decomposing, that means breaking apart. Well, synthesis was the formation of compounds. Decomposition is kind of the breakdown. So if you look, now we're going to have AB, so this is going to be complex. And it's going to be broken down into simple and simple. Okay? This is what we do when we want to isolate compounds. So if we want some pure iron, we're going to take some iron ore or iron oxide, pull it out, break it apart into iron and oxygen. Okay? It's the breakdown, usually, of compounds. So an example of it, I'm just going to kind of write one out here, is if I take water, so this is more complex, it's a compound, I can break it into hydrogen gas and oxygen gas. Okay, now this isn't balanced. Okay, I'd have to put a 2 here and a 2 there, and now it's balanced. But this is the breakdown. So what I've done is take into hydrogen and oxygen gas. Okay, so we have two more reactions left. A single displacement. So these ones are really easy to identify. Basically, it's when you take an element, okay? So you take a single element and you react it with an ionic compound. So you take an element and you put it together with an ionic compound. Now, sometimes this doesn't produce a reaction, but if it does, then what will happen is you will kick out one of the elements in the compound. So if we look at the compound here, okay, BC, that's the compound. What has happened in this reaction, and let me put the arrow in so we can actually see the reaction, is B's been kicked out of the compound, and now it's its lone element, so we have a new single element, and then A has now formed with C to make a new compound. So because there's a particle rearrangement, we know that this is a reaction, and that's a single displacement. And the name kind of tells you you are displacing, so I'm displacing B, and it's a single, I'm only displacing one thing. I'm going to singly displace B, and that's a single displacement reaction. Here's a good example of one. This is an example of how we make a base. You may have heard of acids and bases. So how we make bases, we kind of take metals and we put them in water. So if I take a single element, okay, like here we got some potassium, and I'm going to add it to a compound, water, right? And what's going to happen here is the potassium is going to displace the hydrogen. And the hydrogen is going to get kicked out, and now it's on its own. And now the potassium has bonded with the oxygen and hydrogen that was left, which is called the hydroxide. Okay. So what has happened is basically an element has replaced another element. Okay, and that's single displacement. Now, double displacement. It sounds very intimidating, but it's very, very similar to single displacement. Okay. So what we have here is we have two compounds, okay, two ionic compounds. Okay. And what's going to happen is basically they're just going to switch. So we're going to switch two things, and that's why they call it a double displacement. So C is going to come off, okay? A is going to come off, and then what they're going to do is they're going to flip-flop. So C is then going to bond with B, and I get CB over here. And then A is going to bond with D, and I get AD. So this is very similar to a single displacement. Because I'm changing two things, we call it a double displacement. So this is a reaction that involves two ionic compounds. So the two ionic compounds exchange cations. So they exchange their positive. So if A was positive and C was positive, they would change. Okay? And then B would be the negative or the nonmetal. And they basically just swap positions. Okay? That's a displacement. So here's a good example of one. Okay? Right here. So this is silver nitrate. Okay? So we got silver nitrate here. There's my silver, and then that's a nitrate. And ionic compound, and I got my other ionic compound here. Well, if you remember, silver is going to be a metal, so that's positive. Calcium is a metal. Okay? Chlorine is a nonmetal, so it's going to be negative, and nitrates are nonmetals as well. So what's going to happen here is the positives are just going to swap. Okay? Calcium was bonded to chlorine, okay? But it's now going to bond to nitrate, and I got calcium nitrate. Then I take my silver, which is also positive, and it's going to bond where calcium was, and it's going to go all the way down over to chlorine. And now I get silver chloride. So this is kind of just basically a double displacement. Two things have switched. Calcium has switched spots, and silver has switched spots, so that's why we call it a double displacement. Okay, so this is kind of just a summary, kind of a picture representation. So this is a synthesis reaction. Okay, again, they call it a combination, but a synthesis reaction where you take two things and you combine them to make something more complex. The exact opposite is if you break it apart again. If I take that complex thing and now break it into simple and simple. So these two reactions are opposite of each other. Then I've got a single displacement, which means that I have a compound plus an element, okay? And that element is going to replace one of the elements in the compound. So the red got kicked out, and now it's by itself, and then the yellow bonded with blue and made a brand new compound. And then a double displacement is when two things switch. So a single displacement is when one switched, so really only the yellow switched, okay? In this case, we're going to have the yellow switch as well as the red switch, so we call it a double displacement, and we make two brand new compounds. Okay, so just kind of finish up, and don't worry about these questions. We're going to just explain just the general formula. With a synthesis reaction, it's A plus B leads to AB. Decomposition is AB leading to A plus B. A single displacement would be A plus BC, and then the A is going to replace the B. So a single displacement, I would get AC plus B. Double displacement, we're going to go AB plus CD. So these are my two reactions. Okay. And if this is positive and this is positive, they're going to switch spots, and I'm going to get AD plus CB. Okay. And don't worry about combustion. We'll talk about that in grade 11. Okay, so this is our overview on reactions. I know it was quick, but we're kind of running out of time here at the end of the year. But definitely something that we're going to focus on if you decide to take grade 11 chemistry.